What's up, scholars? Welcome to e-learning day number 1. We're going to start us off with some delicious material. For some of you, it's a little review. Others of you, it's your first time seeing this piece of beauty. But we're going to go right into section 8.6, proportions and similar triangles. Let's remind ourselves what we're talking about here. Proportion is two ratios that are equal to each other. We can have extended proportions that are more than just two ratios equal to each other. We could just continue on forever and ever and ever. We don't usually do any more than 4, because we're not usually talking about more than 4-sided things. But your extended proportion, you know, infinity is your limit. Sky is your limit. And similar triangles, those are triangles that, you know, look similar, except for one's tinier than the other one. They're hard to draw freehand. Whoa, terribly hard to draw freehand. We do know a couple things about them. Why did I make them so skinny? We know that all of their angles are congruent. All their angles are congruent and their sides are proportional. So if this was side, oh, well, we'll just write it. All angles congruent, sides proportional. Proportional. Get back in that groove thing here. Proportions and similar triangles. So specifically, we're going to be interested in what those proportional sides look like in these similar triangles. So let's go ahead and draw ourselves a beautiful triangle so we can talk about it. We have this beautiful triangle ABC. Now, I'm going to tell you we can make a similar triangle with one segment. That's right. One segment is all that we need to make a similar triangle. Now, where we put that segment, obviously pretty important, but all we need is one segment to make a similar triangle. Let me show you how. Shall I? I think I shall. Fabulous. We're going to take one side of the triangle. Specifically, we're taking side BC because it's kind of fun, right? It's like on the bottom of the triangle, the way that we've oriented it. We could rotate this around and do this any type of way, but we're going to take BC as the bottom because that's where it is right now. And we're going to draw a segment that is parallel to segment BC. We did it. Let's call this sucker DE. And with that, we have made similar triangles. How do I know? Well, I made parallel lines. I know that. And in doing so, I made some corresponding angles that were congruent. So I actually already have 2 triangles that are similar by angle, but I get that third angle, very easily by seeing that both of these triangles share angle A. Boom, 2 similar triangles. Triangle ADE is similar to triangle ABC, just like that. And since they're similar, we know their angles are congruent, right? That's how we used to prove that they were similar. And we know their sides are proportional. So we know the ratio of side AD to side AB is equal to the ratio of side AE to side AC is equal to the ratio of side DE to side BC, because the little triangle is similar to the big triangle. Booyah, Grandma. Awesome. So we just talked about describes the triangle proportionality theorem that says if DE is parallel to BC, then those two triangles are similar to each other. Those triangles are similar to each other, so their sides are proportional. And we can even go so far as to say that segment AD over segment DB, the proportion of that segment over that chunk of side, is equal to the opposite side of the triangle. Same idea, which you can't see that way. Haha, but you can see this way. AE over EC. There's some not so fancy algebra that actually takes you from this step to this step, which you are certainly welcome to do. You can also take it on face value. I promise it's true that AD over DB equals AE over EC. Now, if that theorem is true, its converse in this case is actually also true. Now, we remember what converse is. That's when you take the if and you flip them around. So the converse is going to be if those chunks of sides and sides are proportional. So if AD over DB equals AE, is what that should say. AE, good catch, over EC, then those lines must be parallel. Why? Well, if the sides are proportional, then those triangles are similar. If those triangles are similar, their angles are congruent to each other. If those angles are congruent, then those are corresponding angles that are congruent, so we must have parallel lines. Wow! Alright, let's go do ourselves some practice. So let's leave this guy here, keep it, and do some practice. I think I'm going to use blue pen for this practice question. Oh, that's nice, isn't it? Example number 1. Let's draw yourself a triangle. Could be any kind of triangle. And then let's draw a line parallel to the bottom line. Boom, 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 boom. Then let's put some numbers that go on some of the sides of these newly created similar triangles. Let's call this 2. Let's call this 2.5. Let's call this, I don't know, and let's call that 4. Can we solve for x? Oh yeah, you bet your boots. We got parallel lines, which means we got congruent corresponding angles. Congruent corresponding angles. Which means we have similar triangles. Which means we have proportional sides. Which means we can actually compare the one side of the little triangle to that chunk on the bottom of the big triangle. So we can say 2.5 over 2 is going to equal x over 4. And I know how to solve these. You know how to solve these. We're just going to cross multiply. 2 times x, 2x, 2.5 times 4. What in the world? 2.5 times 4 is like 5 over 2 times 4. 20 over 2 is like 10. Oh, cool. 2x equals 10. And then I know what x equals. X equals 5. X totally equals 5. There are actually lots of fun ways you can solve that problem. All of them will get you to 5. Great. Fabulous. I was using the triangle proportionality theorem, which said if we had parallel lines, then we have proportional sides. We could solve for anything we want. Let's do another one that talks about the converse. So draw yourself another triangle. Let's make it a little different, shall we? Slightly different. Let's put a line that looks like it could be parallel, but let's say we don't know if it's parallel. Okay? Let's put some numbers here. Let's call this 5. Clearly not going to draw this to scale. Let's call this 10. Let's say this is 6 and this is 12. And our question is, are those lines that we drew parallel lines? See, now I got to give them points so we can talk about them. Let's call that A and B, and C and D are segment AB and segment CD parallel. I guess it would be is segment AB parallel to CD? Well, let's see. If the sides are proportional, then yes. If the sides are proportional, then the triangles are similar. If the triangles are similar, then their angles are congruent. If their angles are congruent, then we have corresponding angles that are congruent, which prove that lines are parallel. So let's see what we got. Is 5 over 10, is that equal to 6 over 12? Why, yes. Yes, it is. Each of these could reduce to 1/2. So 1/2 certainly equals 1/2. So our answer is yes. Those lines are parallel because their sides are proportional. Now let's go back to that triangle we had before. We could, in fact, add in a third parallel segment. Let's call it X, Y. And if that one's parallel, then its corresponding angles are also congruent. So we actually have 3 similar triangles kind of stacked on top of each other. So we could have a proportionality statement that works for all of those triangles, which would be pretty long, actually. Or we could just zoom in on this little piece. We zoomed way in. And we can make a proportionality statement just about these chunks. From there to there, to there to there, and there to there, to there to there. That's the crux of this whole section 8.6, man. The proportions created by parallel lines chopping up these lines. So let's write that out. That proportionality statement that encompasses everything we've talked about so far. The 8.6 theorem. The 8.6 theorem. Theorem 8.6 says if those 3 lines are parallel to each other, then dx over xb is equal to ey over, no, not ec, yc. yc. ey over yc. Alright, there's one more cool theorem we're going to use, so we'll need some more space to draw another triangle. Voila, our other triangle. Now, follow with me here. We're going to take one of these angles and split it perfectly in half. We have the angle bisector to that angle. Now we're going to draw a line that's parallel to that angle bisector. Our parallel lines. Now, finally, we're going to connect this side of the triangle, extend it through that parallel line we drew. And now, having done that, we have another set of similar triangles. Because these lines were parallel, that means these corresponding angles are congruent. So this triangle on the top is similar to the big triangle. They have these corresponding angles that are congruent, which we made from our parallel lines, and they share an angle up here on the top. So we have another pair of similar triangles. So let's give them all some names and then talk about a beautiful proportion that we just created. And this guy is elegant. Just wait. We have one more angle we need to add to this. So again, these lines are parallel. So we had these corresponding angles that were congruent. We also just made some alternate interior angles that were congruent. Namely, this BCD angle and this BDE angle, our alternate interior angles are congruent. So now we see that these two base angles of this triangle DBE are congruent, which means this triangle here on the bottom is an isosceles triangle. Because isosceles triangles have base angles that are congruent. If it's isosceles, it means its sides are congruent. So BD is congruent to BE, meaning that their measures are equal. So if we go back to our 8.6 theorem, or even more specifically, our triangle proportionality theorem, we chopped the triangle up with parallel lines, and we were able to say that since BE is parallel to ED, AB over BE is equal to AC over CD. But we just showed that BD and BE are equal to each other. So I can actually substitute in BD in this equation. So we'll now have AB over BD is equal to AC over CD. So here's our final cool theorem. Made a smaller little version. Theorem 8.7. If BC bisects angle B, splits it perfectly in half, then the ratio of AB to BD will equal AC over CD. Whoa! Man, that's just gorgeous. That's really, really pleasant. Do a couple example problems. Example number 1. Draw yourself 3 parallel lines. Let's say they're all perfectly parallel. Cool. Then I want you to chop those 3 parallel lines with 2 lines that cross through them. How about line L and line K? Great. We've got 3 parallel lines, and our magical genius tells us that we just chopped those lines L and K proportionally. Let's plug some numbers in and solve for some variables, shall we? Let's call that guy 9, 2x minus 10, 4, and 6. Since we chopped these 3 parallel lines with 2 lines, those 2 lines now have these proportional sections. So we could say that 4 over 6 would equal 2x minus 10 all over 9. We can do some cross multiplying and solve. 9 times 4 is 36. And 6 times 2x minus 10 is going to equal 12x minus 60. Add 60 to both sides. We'll get 12x equals 96. Divide everybody by 12. That, my friends, leaves us with an x equaling, how much is it? How much indeed? Oh yeah, x equals 8. Super chouette. We could even plug x back in. We'll say that section, 2x minus 10, whoops, extra parentheses, what are you doing? 2 times 8 minus 10. Well, that's 16 minus 10. That's 6. Great. That side length would be 6. We are, in fact, geniuses. We're such geniuses, we're going to do one more example. Example number 2, we took another triangle and chopped it with an angle bisector. So these 2 angles are equal to each other, and we know that we made some beautiful proportions. So let's plug in some numbers and solve for some variables using those beautiful proportions. Got this side is 5, this side is 9. That's going to be 14 minus x, and that's going to be x, which actually meant this whole thing was 14. That's neither here nor there because we're solving for variables. We are going to use the proportion that we just talked about. So we know that 9 over 15 equals 14 minus x all over x. We know we can cross multiply and get 9x equals 15 times 14 minus x. We know you can distribute and get 9x equals 15 times 14 minus x. 15 times 14 is 10 minus 15x. We can add 15x to both sides and we'll get 24x equals 210, and we divide by 24. You're right. We're going to get a decimal. Don't worry about it. It's okay. Our decimal is 8.75. Decimals are legitimate numbers too. And we can plug that in and find what the other side was. 14 minus x. 14 minus 8.75, well 14 minus 9 would be 5, so this is 5.25. How cool is that? The coolest. Alright scholars, that's it. That's section 8.6 in a beautiful nutshell. Great job. Wonderful. You know, good things come to those who hustle, so keep on that hustle. Love you scholars. See you next time.